Let's calculate the expectation value of x, or the average of the position, the expectation value of x squared, the expectation value of momentum, the expectation value of p squared, the error in position, and the error in momentum, or sigma x, sigma y, sigma p, or the standard deviation in position and momentum. We're gonna check that the uncertainty principle is satisfied between sigma x and sigma p. We're gonna look which state comes closest to the uncertainty limit, which is h bar over 2, right? So we're gonna calculate these expectation values for the potential v of x equal to 0 between 0 and a. So this is a. So there is no potential between 0 and a, and it's infinite everywhere else. So the particle lives somewhere here. So this is the particle. It's given by this psi sub n function, right? It depends which state the particle is in. And this is x, right? So when I say we're gonna calculate the expectation value of x, it's the same question as where most probable you're gonna find the particle within here, okay, within this region between 0 and a. Where is the most probable place you'll find the particle? So let's remind ourselves what is psi sub n of x. For the infinite square well, we find it to be square root of 2 over a. This is the normalization constant times the sine of n pi divided by a times x. So first thing we have to find is the expectation value of x, which means we're gonna sandwich this between psi star sub n, here we go, the x, times psi sub n of x dx. Because our wave function is not complex in this example, we just can multiply the two functions, right? When we do this, we get 2 over a. This comes from the magnitude of a squared. A is the normalization constant times the integral between 0 and a of x sine square of n pi divided by a x dx. Okay, this is a fun integral. Let's make a change of variable, okay? So here on a side, let y be n pi divided by ax. So dx, just integrate both sides, is equal to a divided by n pi dy, and the limit is, for y, the limit goes from 0 to n pi, right? Because x goes from 0. So when x is 0, y is 0. When x is a, y is in a. So now we're gonna integrate 2 divided by a divided by n pi squared, the integral from 0 to n pi y sine of y dy. So this integral will give us 2a divided by n squared pi squared times y squared divided by 4 minus y sine of 2y divided by 4 minus cosine of 2y divided by 8. We can integrate from 0 to n pi. So putting the integration limits, we have 2a divided by n square pi square times n square pi square divided by 4 minus cosine of 2 n pi divided by 8 plus 1 over 8. Doing some algebra, we get a over 2, and that's the expectation value of x. So if you remember the graph here, so the psi function lives somewhere here, right? Psi sub n, and the expectation value, the average of x, is independent of n. So it doesn't matter which quantum state you are in. You can be in the first quantum state, a over 2 will be your expectation value. You can be in the second quantum state, you can be in the third quantum state. It doesn't matter. All these quantum states have the same expectation value of x. So now let's find the expectation value of x squared. Again, we sandwich x squared between psi star psi and integrate. We get 2 divided by a, the integral from 0 to a, times x squared sine square of n pi divided by a x dx. Using our y variable, we're gonna substitute a y for x and simplify. We get 2 over a times a divided by n pi to the third times the integral from 0 to n pi y squared sine square of y dy. This is a simple integral. So doing the integration, we get 2 times a squared divided by n pi to the third times y to the third divided by 6 minus y to the third divided by 4 minus 1/8, and that's gets multiplied times sine of 2y minus y cosine of 2y divided by 4. We're going to integrate from 0 to n pi. Putting the limits of integration in, we get 2a squared divided by n pi to the third times n pi to the third divided by 6 minus n pi cosine of 2 n pi divided by 4. Simplifying this equation, we get a squared times 1/3 minus 1 divided by 2 times n pi squared. And that's, my friends, is the expectation value of x squared. So now we have to find the expectation value of momentum. That should be easy. What's the momentum? Momentum is mass times velocity, which is mass times dx dt. Right, which is mass times the time derivative of the expectation value of x, which is a over 2, and that's a constant, so this is 0. Okay, so now we have to find the expectation value of p squared, which we have to sandwich this p squared between psi star psi. So psi star of n times p, which is h divided by I ddx square psi sub n dx. You see why this is important, why we sandwich this, because if you don't sandwich this second derivative here, you're gonna mess it all up, and we can't do that. So okay, before you substitute your psi, it's very good to keep it to the last moment. Okay, you're gonna learn these tricks later on because it's gonna save you a whole lot of time. So now, as you see, this is just the second derivative of psi, and psi repeats itself. Okay, so we have IH bar square minus, the minus comes from the I here. Okay, so minus h bar square times 2m e sub n divided by h bar square, that's also negative. Okay, times the integral of psi star sub n psi sub n dx. Well, this is 1, we know that, so that's the good news. So from here we get to this equal 2 m e to the n, which is the same as n pi times h bar divided by a square. There you have it. This is the expectation value of p squared. So now we have to find sigma x. Well, sigma s is the expectation value of x squared minus the expectation value of x squared. No, hold on, that's 0. Sorry, this is the expectation value of the square of the x. Here we go. So plugging these numbers in, we get a squared divided by 4 times 1/3 minus 2 divided by n pi squared. So this is, I'm sorry, this is square. So sigma x is going to be equal to a over 2 times the square root of that, 1/3 minus 2 divided by n pi squared. The expectation value of p, so we have I'm sorry, not the expectation value, the standard deviation of p squared equals to standard deviation of p squared minus the expectation value of p squared. I'm sorry, I call this different. The expectation value of p squared minus the expectation value of p squared. That's the same thing. You see the difference, okay. Anyway, so plugging these numbers in, we get n pi h bar divided by a square, which gives us sigma p, standard deviation of p, equal n pi h divided by a. So to check for the uncertainty principle, we have to multiply these two boxes. So sigma x times sigma p should be bigger than or equal to h bar over 2. That's the uncertainty principle between momentum and position. So is that true? Let's see. So sigma x sigma p equals h bar over 2 times the square root of pi squared divided by 3 minus 2. It's n squared here. Here we go. So we can't calculate this number until we substitute a value for n. So for n equals 1, you can see this is going to be the lowest number. So for n equals 1, we have h bar over 2 times the square root of pi squared divided by 3 minus 2, which is equal to 1.136 times h bar over 2, which we see this is slightly bigger than h bar over 2. It's just a hair, it's just a little bit bigger. Don't like this. .136. Here we go. So for n equal 1, this is going to be the closest to the uncertainty limit.